Welcome back. So in our fourth lecture of the course today, we're going to be turning our attention to non-parametric methods. So this is a large and useful family of methods that cut across both supervised and supervised settings. And today we're going to be looking at a few examples. So this will be a bit more of a grab bag kind of lecture where we'll look at a few algorithms specifically known as KDE, KNN, as well as K-means. So far in the course, the algorithms we've encountered all fall in, or can be categorized all as parametric methods. So what this means is that they assume a specific form or structure for the solution, and then learn the parameters that best fit that data. So for example, the perceptron algorithm assumes a separating hyperplane defined by the weight vector W, and it classifies data points based on whether they fall on one side of that plane or the other. In the case of linear regression, the model assumes a linear relationship between the input X and the output Y, parameterized by the weights W and bias B. And finally, when we last encountered distribution learning, we assumed that data followed a normal distribution with parameters mean, and variance sigma squared. And our task was to estimate the parameters that best describe that data. And so each of these models define a hypothesis class based on specific parameters, which we learned from the data. And so the assumption this assumption of a fixed form is what makes these approaches parametric. For example, last week we learned how maximum likelihood estimation could be used to estimate the parameters of a multivariate Gaussian distribution. So this approach was well suited to this data set on the left here. In real-world scenarios, though, data doesn't neatly fit into the assumptions of parametric models, such as the multivariate normal distribution. So the scatter plot illustrates the challenge here, because it's clearly not Gaussian. It doesn't seem to follow any one distribution in particular. And so parametric methods, because they assume a specific form and estimate parameters like the mean and the covariance matrix, those parametric methods would struggle to capture the intricacies of the distribution on the right. And so kernel density estimation, or KDE, is a non-parametric way to estimate the probability density function of a data set. And so in this context, we're given a set of samples x1 through xn, each of which belongs to the set of real numbers in a multidimensional space of dimensionality D. But then we're interested in the probability density at some arbitrary point in the domain or feature space. And so in KDE, we use a kernel function to interpolate between points in our data set. So intuitively, we place a small smooth blob or kernel function centered at each data point that we have, and then sum these to create an estimate of the overall distribution. So wherever we see a data point, we drop a kernel, and by summing the contribution of these kernels, we get an approximation of the density across the feature space. And so areas where points are densely packed will have overlapping kernels, like here in the center. So this will create high density regions, which are shown here in red in the figure here in the bottom. On the other hand, where points are more spread out, like on the periphery, this will correspond to less dense regions or lower probability density in our kernel density estimate, shifting us into the orange, yellow, and even white zones. So the idea is that KDE allows us to estimate density without making strong limiting assumptions about the shape of the underlying distribution. And so mathematically, the density at a point XO is the sum over the kernel function evaluated at the query point XO and each sample point XI. A length scale parameter, lambda, is introduced to control the amount of smoothing applied to account for different spreads between different distributions. In KDE, we typically are interested in symmetric and shift invariant kernels, such that its output depends only on the difference between the query point and a given sample point. In math, this would appear as follows. So yeah, the output of the kernel function depends only on the difference between the query and the sample scaled by this length scale parameter. And so in order for this estimator to represent a true probability density function, the area under the curve of the kernel function must sum to 1, and it must be non-negative. So a common choice is the Gaussian kernel. I'll speak a little bit more about the length scale parameter because it's crucial in our ability to approximate the empirical distribution. So dividing by lambda adjusts the scale of the data with respect to the kernel. And so in the figure, the idea is that this gives the kernel an appropriate spread around each data point. So if we had a lot of data points close together, we would probably choose a small length scale. Whereas if our points were very far apart, we would select a large length scale. Typically in kernel density estimation, this lambda parameter is fixed. We select one lambda parameter for the whole data set. Although there are some approaches to have where you vary lambda over the data set, but those are less common approaches, more advanced approaches. But yeah, so the length scale is often referred to as the bandwidth because it controls how fast our approximation can change as we move over the domain of the data. If the length scale is too small, the resulting density estimate will be spiky. It'll be sensitive to noise. On the other hand, if it's too large, the estimate will be overly smooth and miss finer details in the data. And so as the final comment, because the length scale is applied by dividing the features of the data, it affects the density that's evaluated. It affects the evaluated density. And so we have to compensate for this by applying the division outside the sum as well. So for example, if we selected a large length scale and we're using a Gaussian kernel, the difference between the query and the sample would be small, and therefore each point would contribute a very large density. And so we divide by the length scale again to counteract that effect. In multivariate cases, the length scale can be a vector. So this gives us different levels of smoothing in different directions. And there are some heuristics for selecting the bandwidth, such as Silverman's rule or Scott's rule. And these heuristics are often based on the number of samples and the number of features in your data. So the scikit-learn documentation gives some examples of admissible kernels for density estimation. The Gaussian is most common, but there are some other options like the top hat and the Epinechnikov kernel. The exponential, linear, and cosine are less common choices. But the key is that they share these properties of being symmetric and shift invariant, as well as non-negative and having a total area of the curve of 1. And so to connect back to what we covered last time with maximum likelihood estimation for distribution learning. Last time we saw how the callback-Leibler divergence provides a measure of how one probability distribution diverges from a reference distribution. And we thought about what to do when we don't have that reference distribution, because that's something that's generally unknown. And so when we don't have an analytical form for the reference distribution, we can approximate it using KDE. And so in this example, the true underlying distribution shown in gray, gives us a bunch of samples shown by these black markers. And we can use these samples to reconstruct an estimate of the probability density function. And so here, the input distribution is estimated using different kernels, specifically the Gaussian, the Toppat, and the Epinetchnikov kernel. And so the idea here is that KDE gives us a flexible way to approximate that true or reference distribution P. And then we could use this to compare it to another distribution Q, which could be our model. And so yeah, the choice of kernel bandwidth will impact the quality of the approximation and therefore the accuracy of that divergence calculation. Right, so that was one example of a non-parametric method, specifically for distribution learning. And for the rest of the lecture, we'll encounter two other examples. Next, the k-nearest neighbor algorithm for classification, which is a supervised learning problem, as well as k-means algorithm for clustering, which is an unsupervised problem. Okay, so starting off with k-nearest neighbors. So this scatter plot depicts a classification problem where the two classes represented by these red and blue points, but they're not linearly separable, like we saw when we covered the perceptron. So there's no single straight line or hyperplane that can perfectly separate the two classes over the domain of the data. So you can see this from the fact that the red and blue points are intermingled within the different regions. And so to handle problems like this, we need a classifier with an irregular decision boundary. And so what can we do when we're faced with a data set like this? And so a reasonable assumption is that labels are likely to be the same when points are close to one another. And so what I've shown here is a Voronoi diagram, and this helps to give a visualization of the idea. So each cell in this diagram contains one of our training examples, and so everywhere within this cell are closer to that specific training example than to any other point. And then points that lie along the Voronoi line segments are equidistant to two or more training examples. And so this is the idea behind the one nearest neighbor algorithm, where we would classify a new point based on the label of its nearest training example. So for example, this black point would be classified as red because it is closest to a training example that was labeled as red. And so with one nearest neighbor, every training point is its own closest neighbor. So this method would always have zero training error because a point is always closest to itself. This doesn't necessarily mean it would perform well on new unseen data, though. And so at a high level, k-nearest neighbors works by finding the k closest training example to a new point based on a specified distance metric. And so this example, you can see where k is equal to 3, meaning that the algorithm will look for the 3 nearest points in the training set and classify the new point based on a majority vote of those 3 neighbors. So an important characteristic of KNN is that it doesn't require any training, not in the traditional sense. So this is really unlike models that process and learn from the data during training. KNN simply stores the entire data set. And so all the computation happens at prediction time when the algorithm needs to determine which points are closest to the new data point and what the majority class label is. And so generalizing KNN a value of k greater than 1 makes it more robust to noise and outliers because we're considering multiple neighbors rather than just the single closest one, as in the case of one nearest neighbors. And so finally, an essential component of k-nearest neighbors is the distance metric we use to determine which points are closest. And so two common options are the Euclidean distance, or L2 norm, and the Manhattan distance, or L1 norm. So I've said before that K is a hyperparameter, and it plays a crucial role in shaping the model's decision boundaries, and also affects something called the bias variance trade-off. So bias refers to the error introduced by approximating a real-world problem with a simplified model. A high bias model tends to underfit. So this means that it oversimplifies the data. It fails to capture important essential patterns. So this is right. And so variance, on the other hand, refers to how much the model's predictions change when it's trained on different subsets of data. So a high variance model tends to overfit, meaning it models the noise in the training data rather than the underlying distribution. And so from this slide, when k is equal to 1, we can see that the decision boundary in black here is really flexible. It allows following the training data very closely. And so this would be an example of a low bias but high variance model, which we would expect to overfit and perform poorly on new data. On the other hand, if we set k to 100, the decision boundary is much smoother. And so this is an example of high bias but low variance, because we would expect that the model to actually underfit the data. And so in practice, we want a moderate value of k. For example, using k of 10 in this example to reduce, I guess, to optimize the trade-off between the bias and variance for better performance on that unseen test data, which is what we really care about. And so choosing the right k is crucial for finding that balance. All right, so what's the catch? Well, its complexity is less than favorable. There's no real computation involved during the training phase. We simply store all the data in memory. As shown in the table, the time complexity for training is 0. However, the space complexity scales with ND, so it's linear with both the number of features N and number of features D. So this is a huge drawback of KNN. You have to store the entire data set in memory, and you have to keep that memory around whenever you want to classify a new point. And so all the computational work really happens in the testing phase. So every time we classify a new data point, we need to compute the distances between the new point and then every point in the data set. So this scales with both the number of samples N and the number of features D. And then after calculating the distance, they need to be sorted to select and find those k nearest neighbors. So this sorting step has a complexity of n log n, but this can be improved to O of n log k using some efficient sorting algorithms. So the total prediction would usually be benchmarked at nd plus n log k. However, since k is usually much smaller than n or d, the term n log k is usually negligible in comparison to nd, and so the overall complexity is generally approximated as OND. But if you selected a large k, that last term would be significant, and this OND would no longer hold. Yeah, just to sum up, so k affects not only the accuracy of k nearest neighbors, but also the computational complexity that can be expected. Right, so how well does it work? Well, for that, there's a very standard benchmark that algorithm designers tend to evaluate their models on. Specifically, the MNIST data set is a well-known benchmark in machine learning. And so it consists of these black and white images of handwritten digits from 0 to 9. So the data set, there's 60,000 training examples and 10,000 test examples. And each one is represented by a 28 by 28 pixel image. So we've got 784 features per image. And so MNIST is usually thought of as the canonical easy machine learning task. It's really widely used as a standard standard means of evaluating classification algorithms. So Jan LeCun, who originally put forward or contributed the MNIST database as a benchmark, has been keeping a leaderboard on his website. And I took a few snapshots, specifically the early models involving linear classifiers like the perceptron we would have encountered last week, and then k-nearest neighbors, and then the state of the art involving convolutional nets, which we'll start talking about in the later part of the course. And so it's surprising is that the k-nearest neighbors performs pretty well on this benchmark, even though it's so simple. So in this table, when this Euclidean distance or L2 norm is used, KNN achieves a test error rate of 5%. And then if you do a little bit of processing, you can get that down to 2.4%. And this is remarkably competitive with the more advanced algorithms involving convolutional nets. It's much better than the linear classifiers, which can be pretty terrible, getting error rates of around 10%. But yeah, still not as good as the state of the art, but within that ballpark. So yeah, it achieves surprisingly good results on MNIST. Considering its simplicity. And so why might that be? There are some theoretical guarantees for k-nearest neighbors, and they relate KNN's performance to that of the Bayes optimal classifier, which is something that achieves the theoretical minimum possible error rate. And so the reason why the Bayes optimal classifier is the theoretical best you can do is because it outputs the most likely class for a given point with knowledge of the true underlying distribution. So specifically, the Bayes classifier minimizes the probability of misclassification by making predictions based on the true posterior probabilities of the labels, which assume perfect knowledge of the underlying distribution. So yeah, the Bayes optimal classifier is essentially got this oracle-like status where it has information about the distribution that classifiers don't normally have. So it serves as a kind of benchmark of like the best you could possibly do. And so, in other words, given a point X, the classifier, the optimal classifier assigns it to the class that maximizes the probability of the label Y given X and the distribution P. This is mathematically represented by this equation here. So this classifier minimizes the probability of misclassification, meaning that its test error rate is the lowest we could possibly achieve for a given problem. And so we call that the Bayes error rate and denote it by epsilon. And so this is the expected error when we always choose the most likely label given the feature vector. Yeah, so Bayes classifier is the theoretical upper limit on accuracy. No other classifier can achieve a lower error rate than that. And so a fundamental theorem concerning KNN is due to Cover and Hart. And their theorem tells us that in the limit of an infinite number of samples, the error rate of one nearest neighbor is bounded by twice the Bayes error rate, adjusted by a factor involving Bayes error rate. And so what this means for k nearest neighbors is illustrated in this figure here on the right. So the gray dotted line denotes the Bayes error rate, uh, and the black solid line denotes that theoretical upper bound on the one nearest neighbor error rate. So the one and n error rate is bounded from below by the Bayes error rate. So it can't do any better than that. But the error rate of the one nearest neighbor classifier is also bounded from above. So the actual one and n classifier may fall within this shaded region. Yeah, and but it won't fall out here. It won't live in this region. So yeah, and then if the Bayes classifier has a 50% error rate, so it's essentially just guessing randomly in binary, in binary classification, then both the Bayes and one and n classifiers are essentially making random predictions. So they would both have 50% error rate in that case. And so you might be wondering what happens after 50% error rate, but the Bayes error can exceed 50%, at least in the binary classification setting, because the binary classifier always chooses the class with the highest probability. So this ensures that its error rate is less than or equal to 50%. Yeah, if the error were greater than 50%, you would simply flip the predictions, would lead to better performance. So this would contradict the optimality of the Bayes classifier. So there's no real situation where the one and n would exceed the Bayes classifier in terms of performance when the Bayes error is greater than 50%, because that scenario is kind of nonsensical. And so an important thing to note is that, that theoretical guarantee was derived in the context of an infinite a number of samples. But in practice, we're working with a finite number of observations. We don't have an infinite amount of data. And this becomes a problem for training the classifier on high dimensional data. And so one implication for higher dimensional data is that the distance metric actually becomes less meaningful. So if you have a data set where points are uniformly distributed in a high dimensional space, the difference in distances between the closest point and the furthest point actually go to zero as d increases. And so the reason why this is that as dimensionality increases, each of those squared terms in the Euclidean distance metric contributes to the overall distance, even if the individual differences are small. And so when d is large, even random differences across many dimensions add up. And so this makes distances similar. And so in this scenario, the distinction between near and far really loses its value, and therefore the concept of nearest neighbors isn't quite so meaningful. Another thing that happens is that as the number of dimensions grows, the space grows exponentially, but the number of points remains constant. Because we usually don't have the luxury of an exponential increase in data to match the dimensionality. And so this leads to a phenomenon called sparsity. And so here, points in the data become increasingly far apart as the volume surrounding each point expands rapidly. For example, shown in this progression from a one-dimensional cube to a two-dimensional cube to a three-dimensional cube. And so in sparse data, most of the volume is far from any data point, and so this makes it challenging to find those meaningful neighbors they're actually close in a way that's practical. And so it turns out that there is a lower bound on the number of samples we need to reach the theoretical limit established by Kover and Hart, but it depends exponentially on the number of samples. So basically, 1 and n can approximate twice the Bayes error rate for low dimensional problems or with sufficient data. So we won't get into the proof, but I direct you to the Understanding Machine Learning text if you're interested in learning more about what's going on there. Okay, so that was an example, or KNN is an example of a non-parametric classification algorithm. So a non-parametric supervised learning algorithm. And now we're going to look at a non-parametric unsupervised learning algorithm, specifically one for clustering, which is called the K-means algorithm. Okay, so why would we want to cluster when we can classify? Um, well, obtaining labeled data can be expensive, time-consuming. It's especially the case in specialized fields where you might require expert knowledge. And so to get around that, you could do something called clustering, which is a form of unsupervised learning. And here the goal is to actually group a set of objects in such a way that similar objects end up staying in the same group, while dissimilar objects are separated into different groups. And so, yeah, unlike classification, clustering doesn't rely on labels. It just seeks to find structure in the data by organizing it in some meaningful way. Um, so yeah, as you can see in this example, the data points have been grouped into 3 clusters, even though we don't have any labels. And so this is the core idea. We're trying to find patterns and relationships in unlabeled data. So to provide a real world example, here this was taken from an actual research paper published about 15 years ago. K-means clustering was used to group neurons based on their temporal activity patterns. So this plot here is a heat map of neural activities over time. So each row is a neuron, and time is represented along the horizontal axis. So bright points indicate that a particular neuron is firing very rapidly or has a lot of activity, whereas dark regions indicate that that a given cell or neuron is not firing very much at all. So yeah, K-means clustering was applied to group this set of neurons based on their temporal activity patterns. And so after clustering, neurons were sorted first into their respective clusters. So this cluster 1 above the red line, cluster 2 in between these 2 red lines, and then there's a few smaller clusters that are given at the bottom of the plot. And then they were sorted again within each cluster by how strongly their activity corresponded with the mean activity trace of the cluster. So this sorting we can really see in this neuron-neuron correlation plot here. So we see distinct blocks that represent high correlations within clusters. And so intriguingly, even although these behavioral the behavioral state traces whether the animal was running or grooming, running in red and grooming in green. So those state vectors weren't used in the clustering process, but the clustering results exhibit some correspondence to behavioral states. For example, this cluster 2 responds uniquely, fairly exclusively to when the animal is grooming. You can see that here, and then again here, and again over here. And that's not something that cluster 1 really does, or does as regularly or as predictably. And so even though those behavioral state vectors weren't used in the clustering process, there's still a correspondence between the clusters and the behavioral states. So the algorithm wasn't given this information, but the clusters, it found, still related to the animal's behavior. And so so that's quite a compelling result, is that an unsupervised learning algorithm can recover things, can recover correspondences that it wasn't given. And so given that evidence of the real world value of clustering, the authors went back to figure out which neurons or the spatial positions of specific neurons in each of the 2 clusters. So they created a false color image where individual neurons are colored based on their cluster identity. And what's fascinating is that the neurons in these 2 clusters occupy different spatial regions within the motor cortex. So this suggests that, at least in this region of the brain, there seems to be a spatial organization that reflects the functional roles of neurons, specifically related to the animal's behavior. All right, so to introduce the clustering problem in a general sense. So the setup is that we're given a set of n observations, and the aim is to partition these observations into groups or subsets based on some measure of distance or similarity. So the function, that function f plays a key role here. So this could be a distance function or a similarity measure. If f is a distance function, it has to satisfy certain properties. For example, it's symmetric, meaning that the distance from point x to x prime is the same as that of x prime to x. And the distance of x with itself is 0 for all x. It also has to satisfy the triangle inequality, so the distance of x to z is no greater than the sum of distances from x to y and from y to z. On the other hand, if f is a similarity measure, it maps to values between 0 and 1, where 1 represents perfect similarity or the similarity of an object with itself. And so, right, I said the goal of clustering is to partition the data set into a set of k subsets, C1 through CK. And yeah, what do we want about each of those subsets? Well, we typically require that each observation belongs to exactly one subset. So this means that subsets are collectively exhaustive, so all data points are assigned to a cluster, but the subsets are also disjoint. So no data point can belong to more than one cluster. And so the outcome of a clustering algorithm is highly dependent on how we actually define similarity, what we mean by similarity between objects being grouped. And so a given data point can be clustered in multiple equally valid ways, depending on how we define similarity. So for example, if we were given data set with two features that looked something like this, we could come up with two different clusterings, well, at least two. This top one would emphasize something called linkages, which I won't get into. But the bottom one would emphasize that Euclidean distance metric that we discussed. So yeah, the similarity metric is absolutely crucial for determining the output of the clustering algorithm. So in k-means clustering, the goal is to group points into k clusters in such a way that the points within each cluster are as close as possible to one another. And to formalize this, we use a cost function, which is what k-means tries to minimize. And so the cost function is based on the average pairwise distances between points in the same cluster. Specifically, for each cluster Cj, we compute the sum of the squared distances between every pair of points within that cluster. Such as shown in this formula here. And so the cost of a cluster Cj is the average of these squared distances. And so the objective of k-means is to find the partition of the data set that minimizes the total cost across all clusters. And so to give an example of this, we look at the scatter plot here. We have two clusters, cluster 1 in red and cluster 2 in blue. And so in cluster 1, we have points x0 and x1. And for cluster 2, we have x2 and x3. So for cluster 1, the cost is calculated based on the distance between x0 and x1, which gives us a cluster cost of 0.032. Similarly for cluster 2, The distance is based on x2 and x3, and this gives us 0.036. And so the total cost of this clustering solution is 0.068. So we can contrast this with a different clustering solution, and immediately see how this is less preferable in terms of the k-means class function. So the reason why this is that the points within a given cluster are further apart. And so this increases the average pairwise distances between points within the clusters, and therefore the overall cost is higher. So yeah, the cost of cluster 1 is 0.5, and the cost of cluster 2 is 0.291. And so the overall cost is 0.791, which is much worse than what we had before. And so in order to get to a point where we can find clusters that are lower cost and minimize that objective, something that's really convenient is that it turns out that the sum of squared pairwise distances within a cluster, shown here, is actually proportional to the sum of squared distances to the cluster centroid. So I've denoted that mu sub j, and so the centroid is the mean of the coordinates of a set of points. And so the k-means objective can therefore be rewritten to minimize the sum of squared distances to the cluster centroid, averaged over all clusters. So yeah, in k-means, we partition the data into disjoint sets, and then each set is represented by its centroid, mu j. Okay, so we understand the k-means objective, but now the key question, right? How do we minimize it? And so, we might think about trying a brute force search, just exhaustively checking every possible way to assign points to clusters. But there's a big problem because there's actually k to the n possible combinations. So the number of possible combinations grows exponentially with the number of points and the number of clusters. So yeah, brute force would really only be feasible for very small data sets. And in practice, this very quickly becomes completely computationally intractable. So another idea might be to try to use partial derivatives or gradient descent. This works well for a lot of optimization problems, but k-means has a bit of a unique challenge in that it uses hard membership assignments. So what this means is that each point is assigned exactly to one cluster. So the gradient is non-smooth. And those gradient-based methods that we've been using really won't be of much help. Another problem is that the k-means objective actually has multiple local minima, so it's not even convex. Okay, so to solve k-means, we actually rely on some heuristic algorithms, the most common of which is known as Lloyd's algorithm. And the idea here is to iteratively refine the clusters. It doesn't guarantee a global minimum, but it'll get us to a minimum. And so how this works is that we start with a data set of n points, a data set D of n points, x1 through xn, where each, x1 through xn, where each element xi is belongs to R to the D. And then we also provide a specified number of clusters k that we want. And so given this information, the algorithm will output a partition or the data set into those k clusters, C1 through CK. And so how it works is that the algorithm begins by just randomly initializing a partition, creating an initial partition C0. So just randomly assigning points to one of the k clusters. But then the core of the algorithm is an iterative loop that actually repeats until the clusters stop changing. So on each iteration, the algorithm updates the clusters in two steps. First, for each cluster Cj, we compute the centroid mu j, And so this is just the mean position of all points in the cluster. So this formula is what we saw before, the average of all points in the cluster. So this step moves the cluster centroids based on the current members of each cluster. And then once the centroids are updated, the points then get reassigned to the cluster whose centroid is closest to it in terms of Euclidean distance. So essentially, for each point xi, we find the nearest centroid and move the point to that cluster. And so this step updates the cluster membership based on proximity to the centroids. So the algorithm continues to iterate between updating the centroids and reassigning the points to create new clusters until it converges, meaning that the cluster assignments are no longer changing from one iteration to the next. And once this happens, the algorithm terminates and we return the final partition. So in the Introduction to Statistical Learning text, there's a great example of how this works. So it starts off with a data set where there's no assignments, no cluster assignments whatsoever. And then the first thing it does is just randomly assign points to a given cluster. In this case, we provided a k hyperparameter of 3. The next step is to compute the centroids of that cluster. And so this is denoted by these circles here, where we, the centroids are pretty close to one another because we just randomly selected the points. So we wouldn't expect the centroids to be very different. In the next step, we reassign the points to a given cluster based on their distance to the cluster. So for example, this point here was labeled from pink to orange because it's closest to orange. And yeah, it's not as close to pink and not as close to green either. And then we can then iterate Lloyd's algorithm again to update the centroids given those new memberships, given those new clusters. So this moves the centroids to the center of those clusters, which kind of reflects where we would expect them to be. And then this last step, we reassign points based on, again, which centroid is closest to it. So we can see a few samples that changed hands here. Specifically, there were some orange points here that were reassigned to green because they were actually closer to the green centroid than to the orange centroid. So in k-means clustering, that choice of k, the number of clusters, is pretty crucial, but it's also one of the algorithm's key limitations. So as changing the value of k leads to very different clustering solutions, as you can see here. So for example, with k is set to 2, we see 2 distinct clusters. But then as we increase k from k to 3 or 4, we start to partition the data in entirely different ways. So we have to predefine the number of clusters, but this is a problem because we don't know what the true number of clusters should be in advance. Another significant limitation of k-means is that it's sensitive to feature scaling. And so since k-means relies on that Euclidean distance metric to determine cluster membership, the algorithm can be heavily influenced by the scale of the features. So for example, if one feature has a larger variance than another, it'll disproportionately affect the clustering results. So we can have distorted clusters where the distance between points is dominated by the feature with a larger scale, even if it's not the most important feature for clustering. So yeah, for that reason, we often want to apply things like feature normalization before applying k-means. This is especially true when the features have different units like height or weight. Finally, Lloyd's algorithm will really only converge to a local minimum. So this means that the solution depends heavily on the initial cluster assignments. As seen here, different initializations can produce pretty different final partitions, and some are better than others. For example, these solutions here have pretty good, achieve like pretty low costs, whereas these solutions on the corners here are pretty terrible. And so yeah, this is because Lloyd's algorithm optimizes k-means objective iteratively. It doesn't guarantee finding the global minimum. And so in practice, we typically run the algorithm multiple times with different random initializations and select the clustering result that yields the lowest total cost. So this approach increases the likelihood of finding a better, more optimal solution. Okay, so that brings us to the end of the lecture. And I'd now like to just summarize by going over what we learned, as well as trying to make you think about what you could do with this information that we covered today. So we started off by so I guess a key theme was drawing a line between parametric and non-parametric algorithms. So we saw that parametric models have a fixed number of parameters, such as linear regression, whereas non-parametric models, it depends on the data. And so you should be able to give examples of these types of models in both unsupervised and supervised learning settings, and really differentiate between parametric and non-parametric methods. And next, we emphasized looking at both empiric results as well as some of the theoretical guarantees. That even a simple algorithm like KNN classification can perform well on a given data set. It's competitive against some of those state-of-the-art algorithms. So what this means is that KNN is a highly justifiable algorithm to try out on some supervised learning problems as a baseline before moving on to more complicated techniques. We also covered those theoretical guarantees, and you should be able to state the Kober-Hart theorem and understand its implications on real data. And importantly, you really want to be aware of how the theorem connects what we talked about, that curse of dimensionality. So that's a critical factor that causes problems for algorithms like KNN in high dimensional spaces, as at least insofar as we're working with that Euclidean distance metric. You can also now talk about machine learning algorithms in terms of where it falls in the bias variance trade-off. In other words, how it walks that line between underfitting and high bias. Underfitting indicative of high bias and overfitting indicative of high variance. We also covered kernel density estimation. And you could be comfortable using KDE to estimate an empirical distribution from data. And so building on that, you could actually go and apply KDE to compare a learned parametric model against a true or empirical distribution using KL divergence. Moving on to clustering, you could also clearly state the clustering problem. You could explain how it differs from classification. You could also now go implement Lloyd's algorithm for k-means clustering. For KNN, you should understand its computational complexity and be able to implement it with a complexity of at least ONDK at test time, where N is the number of training samples, D is the number of features, and K is the number of neighbors considered. And last but not least, you should be able to design KNN algorithms and also justify your choices, such as the number of neighbors or those distance metrics that you choose. And you can weigh these against the alternative methods. And so you should be able to recommend KNN in appropriate supervised learning contexts, understand its strengths and weaknesses, depending on the particular problem that you have at hand. So that's all for today. Next time, we will be discussing logistic regression.